Thank you. I'm very glad to be here today. And as the previous speakers, I'm going to talk about how to do nonlinear imaging, like contrast imaging, with Cmut probe. So this work was done in France, in the French lab of in Tours. And my talk is about how to look at amplitude modulation, not phase modulation here, but more amplitude modulation for contrast-enhanced ultrasound imaging. So first, there is a lot of things about Cmut nonlinearity. I would just state to this point that the electrostatic force depends on the square of the tension. So therefore, if you look at just a simple case, the pressure measurement with an hydrophone, you can see a lot of harmonics, and compared to a piezoelectric case, the harmonic is very below that. I think that this harmonic mainly came from the nonlinear propagation in water at this kind of pressure level. So this could lead to some issue. For example, if you want to recover the nonlinear behavior of the microbubble, there is two main ways. Today, just the contrast sequences are mainly used. And for example, pulse inversion, you all know about how it works. So for piezoelectric probe, you have a linear probe, or normally almost linear probe, and a linear media. So if you send a signal and minus this signal, summing the echo from a linear media should be 0. If you have a nonlinear media here, it should be different from 0. That's the main things allowing to do some contrast imaging. If you apply this with a Cmut probe, with this nonlinear media and the square dependence of the electrostatic force, you have something different of 0, even for a linear media. So you can't discriminate like this bubble and tissue. Very quickly, we can do exactly the same with amplitude modulation. So with a signal and twice the signal, doing simple operation here. And if we look at the Cmut case, with a nonlinear probe, you should not discriminate the two medium. So what has been done, when I saw the first presentation, I think, okay, that's the same slide. There are some work about Cmut linearization, a lot of work with the pre-compensation of the Cmut nonlinearity, the process, the pre-compensation of the Cmut nonlinearity by applying an input waveform adapted to it, and to see some linear signals after the Cmut. And there are some contrast sequence, like bias voltage modulation, that is specially developed for Cmut utilization. Therefore, you can add on the left the second speaker, and on the right the first speaker, to other methods to linearize or to adapt the contrast sequence. But there is one contrast sequence that we didn't look at. This is what I call the alternate amplitude modulation, and is already used in piezoelectric. It's to use exactly the same signal, but to send it on different aperture. So using half the aperture, like all the even elements, all the aperture, and half the aperture. In a simple case like piezoelectric, you have linear probe, and you are able to detect nonlinear media by doing this amplitude modulation. What is interesting is that even if the probe is nonlinear, because the process of summation is linear, it's always the same signal. You should have, for a nonlinear probe, 0, 2, and for a nonlinear probe and a nonlinear media, something different from 0. This method is already applied on piezoelectric, and even the previous method of amplitude modulation is not really applied now, because this one is more precise. So going to the experimental measurements, first we are going to show some hydrophone pressure measurements. So we have our system with an upper scanner, M to M. This kind of anomaly is used for NDT, but it could be applied to an open scanner, so it could be used for other things. We have a probe here that was designed by the Mixerton and that was created by Vermont. And we have the power supply for the bias voltage. I've been testing, so comparing Cmut and piezoelectric and comparing the different bias voltage. Then I'm going to show some just in vitro imaging with the homemade phantom. With here a tube with contrast agent diluted inside and a wire that is supposed to be linear. I'm going to do some beamforming with an angular scanning from -10 to 10 degrees. And with this bias voltage that is equal to 90% of the collapse voltage of the probe, we try to have the same peak negative pressure, but it's not exactly the same energy because the peak positive pressure is not the same for PZT and for Cmut. Then some simple signal processing, and here are the results for hydrophone measurements. So you can see for here amplitude modulation, the signal and half the signal. When you apply the simple process, you have almost nothing, and you have decreased the fundamental by more than 25 dB. When you look at pulse inversion, it works as well. There are some difference in the spectrum, but it's also 0. And third one, amplitude modulation, but with all the elements and 2 half elements, you have also 0. You can see that even for PZT, this is better than this amplitude modulation. So just to conclude these experimental results, there are very few nonlinearities compared to what we could expect for Cmut. And all the method works, but with very different characteristics. When you applied it with Cmut, you can see clearly that this doesn't work. You have a remaining signal with fundamental and harmonics contents. For pulse inversion, it's done to cancel all the fundamental. So you have a signal at harmonics, but the reflection of this signal will give a lot of nonlinearities, and so a linear target seems to be nonlinear. But when you applied the amplitude modulation, because it's a linear way to do that, you have almost 0 and a very good cancellation, about 40 dB here for the fundamental, and also more than 30 dB for all the harmonics. That's very interesting. So nonlinear signals with a high harmonic to fundamental ratio that is high, and only alternate amplitude modulation works. If you compare it for different bias voltage for smaller, higher excitation, you can see that the results are almost the same. So you have here in the amplitude of fundamental harmonic and third harmonic for different bias voltage before compensation and after processing. So you can see that the decrease of the amplitude for classical amplitude modulation doesn't work. For pulse inversion, there is always the second harmonic that is doubled, and for alternate amplitude modulation, for all the bias voltage, the amplitude decrease for all the components. So it works again until high bias voltage at 90% of the collapse voltage. So then just a few images with angular scanning. You can see here the classical behemoth. You have the wire here. Here is just water, so we are going to use water to define noise. And here is microbubble in a tube. And when you compare the image, all the image work for PZT, there are some very small points that are remaining, could be due to beamforming. And when you look at the contrast to noise ratio and the contrast to tissue ratio, you have a big increase of about 30 dB between B mode and alternate amplitude modulation. That's the one gives the best results. if you look, as expected, all the sequence works, but amplitude modulation is the best one. If you look at Cmut, as expected, the first three, so there is B-mode, amplitude modulation classic, and pulse inversion, they doesn't work. If you look at the value of contrast to noise ratio and contrast to tissue ratio, you have an increase of the contrast to tissue ratio until alternate amplitude modulation. So the results are not as good as I expected. An issue is the dynamic range of the open scanner, so it may give some bad points, and the probe is not is a very old probe, so you have some elements that are damaged, so it's very hard to focalize as good as in the PZT probe that is entire. But still, it's really good result showing that you can have a very high contrast to tissue ratio compared to B-mode, like more than 25 dB increase. And what is really interesting in conclusion is that this method, alternate amplitude modulation, already used in actual scanners for PZT, is efficient to suppress linear tissue. It allows to perform contrast imaging with a Cmut probe and does not depend on the Cmut regime. The assumptions still need some more work because we have to go at collapse, but it's directly applicable on actual sensors. That's a very good point because we just plug our Cmut probe and a DC device, and normally we could use amplitude modulation as it's done actually. Further work is in vivo validation with another open scanner, and to perform tissue harmonic imaging maybe. Normally tissue harmonic imaging is done by pulse inversion, but we could look at this. I will add to this to combine, for example, normally alternate amplitude modulation is combined with PI, and it's called CPS. Maybe we could combine alternate amplitude modulation with phase modulation like it was presented before. Thank you for your attention.